question that has been really confusing for me. Explain the concept of time constant and relate these to fast and slow alveoli. So this is anesthetic primary exam question, 40% pass mark. Deranged physiology, incredible explanation. Let's go through the nuggets and then we'll go through the very confusing nuns diagram step by step. Definitions of normal value. So what is time constant? It's the time required for inflation up by 63% to the final volume, or deflation by 63%. So it's a mathematical of a log diagram essentially, and what you want to know is that at one time constant it's 63%. One time constant is 63%. At the second one, what is it? 85 or 86%. At the third one you go 95%, and the fourth one's about 99 or 98. So that's the definition. Now it's a product of resistance and compliance. So what does that mean? That means when you can, in your answer, you can say alveolar time constant T or TAR equals resistance to filling R times compliance to alveoli. Okay, so that's the equation that we're going by. Now for a normal set of lungs, it's good to know that's about 0.1 or 0.2 seconds. So that's the alveoli, to think of it, filling and deflating. Now in the presence of constant flow, poor compliance, this is very important, poor compliance units will have shorter or normal time constant. So you think of it, a lung or an alveoli that's not filling, that is very stiff, okay, it will actually have it will be very fast. It will be very fast. Okay, so that's what it's saying here. The poor compliance will have a shorter time. High resistant unit will have a longer time constraint. Okay, so if something is having high resistance, it will take a lot longer to fill. It will fill. The important thing is it will fill, not like compliance. Compliance won't fill. It can't stretch. But resistance, it will fill, but it will take a long time. And the other thing to understand is the thing called pendeluft. Pendeluft means there's an exchange of gas between lung units with different time constant. So if something has a quicker time constant, the gas basically flows along that. So when flow says gas may flow from lung units with poor compliance into lung units with high resistance, because the poor compliance can't stretch anymore. It needs to go to areas with high resistance. It needs to go somewhere where it will actually fill. So let's go quickly through this diagram. Now you see C times R is 1 second, so that's T. C times R is 1 second, so that's T. You can see both diagrams, the dotted one and the solid one, are the same. No issues there. Now I'm going to skip this one because it can be a bit confusing. Let's go through this one. C times R is 1. Now here we have double resistance. What did we say when there's an increased resistance? It will still fill, but it will take a longer time. How do we know this? Let's look at this. You got resistance is 2 mil in a small syringe. Resistance is 20 mil in a big syringe. So obviously this is low resistance. This is high resistance. So we're focusing on the high resistance. Now watch with me as this guy blows the balloon. Just speed it up because we don't have enough time. Okay, so he's filling up the balloons. What happens? He's blown it. Okay, so this is low resistance. The one on the left is low resistance. The one on the right is high resistance. Look what happens. Ready? Go. What happens? So the low resistance empties quickly, deflates quickly. The high resistance takes longer time. Still does it, but it takes longer time. And note that both have the same compliance. So that's exactly what Nani is trying to say. The compliance is the same, but the resistance is double. What does that mean? It will take longer time, okay? And actually the time constant is 2. So it takes 2 seconds, say, for it to reach 63%. And you can see here that the slope, it still does the volume. Eventually it will do the volume, but it takes a longer time. The slope is slower. So, and this arrow, what's this arrow representing? It's representing the pendeluft, where the gas moves from poor compliance into high resistance. So this is the slow alveoli, and then this is the fast, okay? And so what happens is gas is moving there, because this inflates and deflates quickly, but because this takes ages, right? So it inflates, and then the person basically exhales, but the lung is still, it's taking a slow, it's slow alveoli, and this is the fast alveoli. Okay. Now let's look at compliance. What did we say with compliance? Compliance is the lack of stretchability. So if it's unable to stretch, what happens? You know that the volume is actually going to reduce. So the volume is going to reduce. What's really interesting here is that the compliance is half. That means the time taken is actually half a second. So it's actually quicker. Half a second. It's actually quicker. So it is quicker, but the volume, because it's unable to stretch, is reduced. But you can see that the slope is actually quicker. So it takes less time. So it's actually still fast alveoli, but the volume is reduced. And you can see that's here 63%. Okay. So that's a really good concept to understand. And again, what happens? It goes from low compliance to the high resistance, because this is a high resistance, right? So the air will flow that way. That's why the arrow is there. We can go back to this one. Now this is a bit confusing because we've got both factors changed here. We have half the compliance. What did we say about compliance? You can't stretch it, so the volume is reduced. So again, the volume will reduce, but you have double the resistance. So what happens? The slope is faster, right? The slope is slower. It takes longer time. So you can see it's kind of difficult to see here because the time constant is 1, because 2 times half is 1. So it's really difficult to see. So it's still 63% at 1. But what's important to understand is that the resistance is doubled, so it's going to take a longer time, and the compliance is half, so the volume is less. So if you compare this one to this one, which one's faster? This one, of course, is faster. The number D is faster because the resistance stayed the same. But when you double the resistance, what happens? It takes a longer time. So you can see the slope ever so slightly. The slope is slower here. Also the time constant is half in this one. Now this is a very interesting one. What happens in the first alveoli, which is a solid line, is that the compliance is what? Stay the same. The resistance is doubled. So what did we say when the resistance doubled? It takes a longer time. It still does the volume, but it takes a longer time. So you can see the compliance is quite slow. Sorry, what am I saying? The graph is quite slow. The resistance has caused that to be. And the time constant is 2. So when you go to 2, that's where 63%. So it's taken time there. Now, what happens when the resistance is the same, but the compliance is half? So we said the volume, it can't stretch anymore. It can't reduce, but the resistance is the same, so it's still quite fast. So you can see here with less compliance, it goes to the area with high resistance. So there it goes here with the double resistance. But then slowly, as you have less volumes, it actually goes to the solid line, even though the compliance, so it goes from low compliance to the higher resistance, right? Low compliance to the higher resistance. Here again, it goes from compliance to the higher resistance. Low compliance to higher resistance, low compliance to higher resistance. The arrow is just pointing the other way because low compliance to high resistance. So remember, compliance to high resistance. That's the pendulum. That's the gas exchange, the pendulum. It goes from, what did we say? From poor compliance to high resistance. It makes sense because the lung can't stretch anymore, so it needs to go somewhere. Where's it going to go? It's going to go where an alveoli is still filling. Where does the alveoli take forever? It takes in the high resistance because it takes forever. As you can see here, there's too much resistance. It will still flow, but it will take forever. So that's basically the answer to that question.